Hello, PO chemists. So here we are, we're towards the end of our conversations about acids and bases in terms of looking at it qualitatively. And in class, we finished up by taking a look, I believe, at this problem on the left. So what I'd like to do is finish up with this problem on the right and wrap up the last couple of slides. So let's go ahead and zero in on the problem on the right. So again, what we're trying to determine here is which of the labeled hydrogens, whether it's HA, HB, or AC, which of these three hydrogens is the most acidic. And then if we can figure out which might be second and third, that would be great too. So if we want to go ahead and use our ARIO issue that we have, right, we have ARIO. Hopefully you can see right away that we have some atom differences. Namely, I have the hydrogens on oxygen or on either of these two nitrogens. So based on atom effects, we're going to go ahead and suggest that the HA atom is going to be the most acidic. If we have an H on a more electronegative oxygen compared to nitrogen, then that's going to be able to stabilize the conjugate base better. Furthermore, this atom also has, this particular H also has some other factors going for it. Namely, once we go ahead and deprotonate, so of course there's a lone pair there to begin with, but once we go ahead and deprotonate, we'll have a second lone pair and a third lone pair on that molecule. We'll actually have three lone pairs after it deprotonates. And then we can go ahead and start to do some allylic lone pair moves with our electrons to go ahead and stabilize further the structure by way of resonance. So HA is going to win for two reasons. It has the atom effect and the resonance effect. Now how about the other two atoms? How about the other two hydrogens? We have HB and we have HC. So HB here on this nitrogen, already there is on that nitrogen, if I wanted to draw them in, we have some lone pairs there to complete the octet. Now once that hydrogen goes away, there'll be another lone pair there as well. That lone pair, these lone pairs could go ahead and start to do some resonance structures as well. So the lone pair on this nitrogen compared to the lone pair that would be eventually up here, the lone pair on HB, on the hydrogen down here, on the nitrogen down here, that lone pair would be delocalized. Because this nitrogen is already doubly bonded to a carbon, the lone pair that would end up on the nitrogen after the hydrogen comes off is not going to be delocalizable. They're going to be localized. So for a lack of resonance reasons, we're going to suspect that HC is going to come in third. So putting it all together then, I'm going to say that HB is going to be the second most acidic and HC is likely to be the third most acidic. All right. Both HB and HC, they of course have the same atom effect, but one can do resonance, namely HB, and another one, HC, cannot. All right. So the order will be then HA, HB, followed by HC. All right, so that's enough with taking a look at relative acidities then within the same molecule. Let's go ahead and talk about another effect that comes into play when we look at the stability of conjugate bases. So ARIO does a pretty good job of explaining some of the qualitative aspects that go into determining acidity, but it can't explain everything. For example, in this case, I have tertiary butanol and I have ethanol. If I think about the components of ARIO, the atom is the same, oxygen in both cases. The resonance effect is the same, namely, neither of these conjugate bases could do resonance. There is no inductive effect, right? We don't have any electronegative atoms near the oxygen. And the orbital effect is going to be the same, right? Once I have my lone pair here, I'm going to have sp3 lone pairs, and I would have sp3 lone pairs. So in this particular setup, there's nothing that ARIO is going to be able to do for us. But it turns out that these two molecules do have different pKa's. Namely, tertiary butanol has a pK of 18 and ethanol has a pK of 16. So not a huge difference, But of course, pKa is a log scale, so the ethanol is really 100 times, of course, 100 times more acidic than the tertiary butanol. What might account for the difference here? Well, let's take a look behind these two bullet points. pKa values are often, typically, we're getting these numbers by looking at aqueous systems. So our tertiary butanol and our ethanol, they're both floating around in water solutions. And so the solvent can go ahead and try to stabilize the conjugate base by way of good old IMFs, intermolecular forces. When the solvent interacts with something in the system, with a solute, when there are intermolecular force interactions between the solvent and the solute, we refer to those kinds of interactions as a solvation effect. So we can have solvent stabilizing our conjugate bases in different ways or to different extents. So given the difference we have here, 18 versus 16, somehow, some way, it seems that the conjugate base of ethanol is getting more stabilized by the solvent than is the conjugate base of the tertiary butanol. Let's take a look on the next slide at that effect. All right, so what we're really looking at is what's referred to as ion-dipole interactions. So this is sort of like dipole-dipole, but cranked up to 10. When we think about an ion-dipole, in the present example, we have our ions, the conjugate bases, be it of either the tertiary butoxide or the ethoxide. The IDE ending indicates that we have an anion, right? Just like chlorine becomes chloride when it becomes anionic, tertiary butanol is going to become a tertiary butoxide when it loses its hydrogen and becomes the anionic conjugate base. All right, so we have a difference here. If you look at these cartoons, buried inside of this pretty colorful picture, this is a ball and stick model of tertiary butoxide. And over here I have a ball and stick model of ethoxide. And as you can tell, I have different numbers of solvent molecules surrounding the anionic portion in both cases. So the anionic oxygen is being solvated by fewer molecules in the case of tertiary butoxide than it is in the case of ethoxide. It seems as though I'm able to get more solvent molecules to surround my anionic oxygen. Why is that? Well, it has to do with a factor that chemists refer to as steric hindrance. The tertiary butoxide is more sterically hindered. What does that mean? It's actually a fancy term for a pretty straightforward idea. Tertiary butoxide has the anionic oxygen, and then on the neighboring carbon, there's 1, 2, 3 carbons attached to that carbon that has the oxygen on it. Meanwhile, ethoxide has its anionic oxygen, which is attached to a carbon, to which there is only one other carbon. Of course, we have 2 hydrogens off of that carbon that I'm pointing to now. So there is greater bulk on the back end of tertiary butoxide in a physical space sense. There's greater bulk here than there is with the ethoxide. There's a lot less bulk here. So the anion is able to get surrounded. Let's call these solvent molecules water. So the polar water molecules are able to interact with the anionic oxygen by way of ion-dipole interactions. So the anionic oxygen is my ion, and then something like water, which we know, of course, is bent with its lone pairs, and of course very polar with its partially positive hydrogens and its partially negative oxygens. So the polar water molecule can go ahead and do ion-dipole interactions right there between the alkoxide, the anion, the IDE anion of the alcohol in both cases. But because there is less bulk associated with the anion of ethanol, the ethoxide, because there's less bulk here, I'm able to surround it with more solvent molecules. Again, maybe more water molecules. And these types of intermolecular force interactions, they are stabilizing. They're going to stabilize the system. So as I have more stabilizing interactions, I'm going to get a more stable conjugate base, therefore a lower pKa. And as you can see here, right, the difference isn't huge. When we talked about atom effects, we were seeing differences, on the order of like 30 orders of magnitude. With resonance effects, we were seeing also double-digit orders of magnitude. The inductive effect, less so, maybe 3, 4, 5 orders of magnitude. And the orbital effect kind of varies depending upon what you're looking at. But this solvent effect, this solvation effect, isn't considered nearly as important. So we could almost turn Ario if we want to. We could go from A-R-I, and then we could put in an S. So maybe it's best thought of as Arios. And I put that S in a lower, in lower font to suggest that it's not going to be nearly as important typically as the other aspects of Ario. All right, so that's solvent through intermolecular forces providing some stability to the conjugate base, a process called solvation. All right, we have one last thing to talk about when it comes to acids and bases, and that is the issue of Lewis acids and bases. You hopefully remember the basics, no pun intended, of Lewis acids and bases from your sophomore chemistry class. Remember that a Lewis acid is something that can accept a pair of electrons, and a Lewis base is something that will donate a pair of electrons. So for Lewis, this is the same fellow, of course, of Lewis dot structure fame. For Lewis, everything is about the lone pairs. And the reason I want to bring back Lewis acids and Lewis bases here is because it gives us another chance to talk about curved arrows, okay? Here's a run-of-the-mill acid-base reaction. We can actually think about this as a Bronsted and Lowry acid-base reaction, right? We have our acid H+, and we have our base of water. And as we did before, our base with its lone pair can go after the H of the acid, followed by a second arrow that shows the bond being broken. So this is a Bronsted-Lowry acid-base phenomenon. But we can also think about this in terms of Lewis acids and Lewis bases. So the HCl, which was our Bronsted and Lowry acid, as we can see, because the H of HCl is taking in a lone pair of electrons, we can also think of HCl as being a Lewis acid, and the water donating the lone pair as being a Lewis base. So if you're a Bronsted-Lowry acid or base, you'll also be a Lewis acid or base. Now, sometimes we can't overlap our different acid and base definitions. For example, in this interaction down here, this doesn't really fit into the whole Bronsted and Lowry scheme, okay? But it does fit into the Lewis scheme. So once again, I have water with its lone pair going after BF3. Now, BF3 is a sort of classic example of a Lewis acid. Why is that? You might remember this again from previous chemistry classes. If I were to draw BF3, the geometry is going to be trigonal planar, so that's what I'm trying to draw here, a trigonal planar BF3. So all 4 atoms of my BF3, all 4 of these atoms are in the same plane, and the way I've drawn it, it's perpendicular to the plane of the screen right now. And so this boron in the middle here, it's going to have, if you can figure this out, it's going to have an sp2 hybridization. So what that means is there's a p orbital left over that we haven't touched yet. And that p orbital is perpendicular to the plane of the BF3 molecule. So it's going straight up and down. And so this p orbital is in fact empty, and so it makes a nice spot to do something like deposit a lone pair of electrons, in this case from the water. And then the end result here is that we've created a new bond between the Lewis base of water and the Lewis acid of BF3. Now, one comment I do want to make about the bond that we've created right there. This bond is not a terribly strong bond. It would be inaccurate to refer to this as a covalent bond. It's not going to have the hundreds of kilojoules per mole strength of a typical covalent bond. Oftentimes, these sorts of Lewis acids and Lewis base interactions lead to not new molecules, but people will typically call these a complex, right? This is a Lewis acid, Lewis base complex, not really a new molecule. And as you can see here, we're still considering the molecule to have a positive oxygen and a negative boron, right? So if we did our electron count here, we'd see that boron has 4 electrons around it. Boron is, of course, in group 3 of the periodic table, so it's anionic. Oxygen has 1, 2, 3, 4, 5 electrons around it, so it's going to carry a positive formal charge. So this is probably best thought of as a positive-negative interaction that's done at somewhat of a greater distance than we might think of for even an ionic interaction. So the greater distance here leads to a weaker interaction than we would think about whether we would compare it to a covalent bond or an ionic bond. So that's why I'm using the word here complex, because it's ultimately a slightly less stable structure than something typically associated with an ionic compound or a covalent compound. All right, so that does it. That wraps up our conversations about acids and bases. Hopefully you are getting comfortable with the idea of ARIO. Hopefully you can, through some practice problems, continue working on drawing these curved arrows to represent acid and base reactions. All right, we'll pick up our conversation again in class.